I'm Britton, and I'm very happy to welcome you to our first Open Wednesday this year, our January Open Wednesday class. But before I introduce our speaker, guess what? It's time to turn off your cell phones and turn on your tea coils. Now, I'm very happy to welcome today Charlotte Christensen. She is an assistant professor of physics at Grinnell College, and she is going to be speaking to us this morning on the subject of the dark universe, discovery of dark matter, dark energy, and the fate of the universe. Heavy subject, I think. Charlotte.
Hi, everybody. Is the mic working okay? Yeah. Great. I'm delighted to be here. I've done one class through ACES before, and this is it looks like a pretty similar crowd, a fair amount of overlap in people. So I've been at Grinnell College for 4 years now. My field of research is in how galaxies form. So I run computer simulations that start from very soon after the Big Bang and evolve the history of the universe to present day. Let's see, what else can I tell you about myself? I grew up in Missouri. My parents are both Grinnell alums, class of 1970. And I did my undergrad at Carleton College. I refused to go to Grinnell, since that's where my parents went. And did graduate school at University of Washington, and eventually wound my way back here. All right, so we're going to be talking about the dark universe today, which is a nice way of combining both dark energy and dark matter into one talk. So first of all, let's see, show of hands of who had heard of dark matter before you read this talk. Okay? Who can describe dark matter to their neighbor? Okay, good, this is a good place to start. Let's do the same thing for dark energy. Show of hands if you'd heard of dark energy before this talk. Maybe a little bit fewer people. Can you describe dark energy to your neighbor? Okay, and that's actually one of the reasons I picked these topics is because these are the big mysteries in astronomy. So I will tell you what we know. There's a lot that we don't know. So even if you asked a room of physicists, can you describe dark energy to your neighbor? An honest person would not raise their hand. All right, so you may have seen a figure like this before. You may have heard the basic idea, which is normal matter, atoms, the stuff that makes up you and me, is only a small fraction of the universe. Most of the mass/energy in the universe comes in either, let's see, the form of dark matter here, or dark energy up here. And this is amazing that these two things that we only discovered in the past 50 years, and which we still know very little about, make up something along the lines of 96% of the universe. So that is both astounding and a little bit frightening, and also to physicists pretty inspiring. So I'm going to start by talking about dark matter during the first part of the talk, and then I will switch to dark energy during the second part. I'm going to focus on talking about how these two things were discovered. I'll talk a little bit about the role they play in our universe, and what we know about them, and how scientists are trying to figure out more. All right, so let's start with dark matter. To get to dark matter, we have to start with galaxies. So we live in the Milky Way galaxy, which is a group of stars and also gas, and as we will learn, dark matter. Most galaxies, or many galaxies, look something like this, including our Milky Way. It looks something like this. This is a spiral galaxy. And we only actually recently discovered that there were other galaxies about 100 years ago, around the 1920s. There was this big question as to whether our Milky Way was the only galaxy in the universe or whether there were all other ones out there. And then after we started discovering other galaxies, there's this question of how are the stars orbiting or moving in these galaxies? What are the dynamics of these galaxies? So if we were to look at the stars in the galaxies and track their motion, then you'll see that most of the stars tend to orbit around the center of the galaxy. And they kind of orbit up and down like a porpoise. There are also some stars in the outskirts of the galaxy, in the halo, that orbit all the way around. Sorry about that. And these are orbiting because of gravitational force. And we'll talk a little bit more about that later on. So around 1970, a scientist, Vera Rubin, is trying to understand the dynamics of stars in the galaxy. In particular, what she is interested is understanding how the orbits of stars could play into the formation of spiral arms. In other words, you could imagine one possible theory for how spiral arms formed back then was that stars close to the center of the galaxy orbited faster, and you ended up wrapping up the spiral arm pattern, kind of like a whirlpool. It turns out that isn't the case, but she didn't know that. Nobody knew that at that point, so she was making measurements of the orbital motion of stars. And she wrote a series of papers along this line. I'll read the title to you, if I can read it. Rotational properties of 21 SC, that means spiral galaxies, with a large range of luminosities and radii, from NGC 4605, that's a particular galaxy, to UGC 2885, a different galaxy. Again, very creatively and beautifully named. So before I tell you what she found, I have to tell you what she was expecting to find. And to do that, I want to take us back to the solar system. So when we think about how an object orbits another object because of gravity, we have a really good example with the sun and the Earth. So the Earth goes around the sun because of the gravitational force. If I was to plot up the distance from the sun here and how fast various planets moved around the sun, you'd see that the planets really close in, like Mercury, move a lot faster than the planets close out, like Pluto. And that's because of two things. First of all, the stronger the gravitational force between two objects is, the faster they can move. And you all intuitively understand that because of toys like this. If you stand on this and start spinning around, the faster it spins, the more you have to hang on, the greater that force. So if an object is going very fast around, then there has to be a very strong force holding it in. All right, so that's point number one. The other thing is that gravitational force is stronger close in and weaker far away. So if two objects are very close together, they feel a strong gravitational force. If they're far away, they feel a weaker gravitational force. So what this means is that there's a strong gravitational force between Mercury and the sun. So that means Mercury can go around really fast. Since Pluto's far away, there's a weak gravitational force between Pluto and the sun, so Pluto orbits more slowly. Cool. So Vera Rubin is making these measurements, and she anticipates, just like everybody else anticipates, that we'll see the same thing with galaxies. If you remember back from that picture of the galaxy I showed you earlier on, there were a lot of stars at the very center of the galaxy. So there's a lot of mass there. So we would expect the gravitational force to be very strong at the center of galaxies, things to orbit very quickly around. And out at the outskirts of galaxies, they're far away from most of the mass, so the gravitational force would be weaker and things should be moving more slowly. And you'd get some diagram that looked like this. That's not what she found. She found rotation curves that looked like this. And in fact, I will read a sentence from the abstract that I showed you earlier in this paper, which describes what she's seeing here. So, spiral galaxies of all luminosity, let's start at the top. All curves show a fairly rapid velocity rise out to velocity of 125 kilometers per second at 5 kiloparsecs. So this is distance from the center here. This is velocity at which things are rotating. So as you move out to the center, there's a rapid rise to velocities of around 125 kilometers per second. And then there's a slower rise thereafter. So then things tend to gradually level off. Most rotation curves are rising slowly, even at the farthest measured point. So right here, this curve is still rising slowly, even out till here. Neither high nor low luminosity spiral galaxies have falling rotation curves. So in other words, we don't see a drop-off like expected. And so, she extrapolates, spiral galaxies of all luminosities must have a significant mass located beyond the optical image. And what she's saying right there is there has to be mass that we can't see. And that's the dark matter. So to give you a slightly different image of this, here's a galaxy here. Stars are orbiting. Here's a distance from the center. This is plotting the velocity at which they're going all around. What we would have expected if all the mass in the galaxies were made up of stars is rotation curve that declined after we got out past where all the stars were. Instead, we see this rotation curve that remains really constant, even though we can't see any mass here. There has to be stuff here. Okay, so that's where the name dark matter comes from. It's matter, it exerts a gravitational force, but it's not emitting light. We can't see it. If I were to try and do an artist depiction of the stuff that we can't see, it looks something like this, a giant halo of mass that surrounds a central little pinprick of stars, what we see as the visible galaxy. So this is cool stuff, and if we were to actually measure out how much of the mass in the galaxy consisted of dark matter as opposed to regular matter, the stars, we'd see that there's about 5 times more dark matter than there are stars. So that's huge. And when I talk about what are the implications of dark matter, one of the big implications is in how galaxies form. If you have 5 times more mass as dark matter, that's going to drive the formation of the galaxies. Where the dark matter congregates, that's where your galaxy is going to form, in the very center of it. So we've done simulations that match, not me personally in this case, but I've done similar ones, that match galaxies like the Milky Way. Here's our Milky Way galaxy. All of these little points out here, these are observed dwarf galaxies that are orbiting around the Milky Way. So this is what we detect when we measure where optical galaxies are. If I compare that to a simulated Milky Way, here I'm showing the dark matter. And you can see that there's a whole bunch of dark matter out here. There's more at the center where there's the Milky Way. And then there are all these little halos of dark matter. Some of those have stars in them, what we see as galaxies. Some of those are entirely dark, just little halos of dark matter out there. Think on the order of 100,000 times the mass of the sun in this cluster of dark matter. All right, so that's just on the galaxy scale, but we can also look at the universe scale. So here is what a map of where all the observed galaxies are in the universe. To help you interpret this, we live right here, and we're looking out in that direction in a V, and we're looking out in this direction in a V. So these galaxies out here are far away from us, so we're looking back in distance this way. And although it isn't quite clear, each of these is actually a very small point. So these galaxies can tend to cluster together in groups. And you also see that there's this filamentary structure here. To actually generate this structure, we need dark matter. So this is a simulation that was run using dark matter, assuming that dark matter interacts through gravity, and they were able to recreate the same filamentary structure that we see in the actual universe. So this is a prediction from a simulation of what the actual mass distribution in the universe looks like. It's pretty cool. All right, so this is amazing stuff. Think back to 1970. In that time, a whole new area of physics and astronomy has been formed. And Vera Rubin really led that push. Unfortunately, she died about a year ago, December 2016. And truly unfortunately, she was never awarded the Nobel Prize. The Nobel Prize is not awarded posthumously, so she will never receive one. Which is tragic when you think about the fact that this is one of the major discoveries in astronomy. So while Vera Rubin came up with the best possible evidence for dark matter and really launched this field, I should also mention one other person who first posited the idea of dark matter. This guy here is Fritz Zwicky. And in 1933, he actually noticed some similar strange behavior looking at galaxies. So what he was doing was he was looking at clusters of galaxies. This is the Coma cluster up here, what he was observing. Each of these fuzzy blobs is a galaxy, and you can see they're all grouped together. From those previous slides, you know the galaxies often come together in groups. What you can't see here is that there's also a whole bunch of gas in the Coma cluster. It's very hot. It emits in the X-rays. So by looking in other wavelengths, he was able to observe this very, very hot gas. And what he noticed is that this gas was really hot for it to be found within this cluster. The gas would have to be gravitationally attracted to the cluster in order to remain in it. Otherwise, it was so hot it would float away like a hot air balloon. So the fact that this cluster was able to retain this very hot gas implied that the cluster had to have a lot of mass, more mass than he could account for from all the stars and galaxies. So this is another piece of dark matter. So he made this observation. He says, this is really strange. He talks about it. I'm actually not sure if he publishes it, but he talks about it. And you can kind of tell from his picture, this guy is a bit of a crank, a very brilliant guy, but brilliant guy with lots of ideas. This idea never really caught hold for various reasons, and it was only 40 years later with Vera Rubin's work that we finally truly delved into dark matter. All right, let's see. Okay, so here's this next question. What actually is dark matter? We kind of talked about how it was discovered and talked a little bit about the role it plays in galaxy formation. So the next question is, well, what makes it? So one idea was maybe there's actually no such thing as this dark mass that lives in the outskirts of galaxies. Maybe the simplest explanation is just that gravity works weird at large distances. We can only make very precise gravitational estimates on smaller distances, so maybe it's just that when you get out to the outskirts of galaxies, that's so far away from most of the mass, maybe the gravitational force is actually stronger at those distances. This is called a modified Newtonian gravity or something, a Mond theory. But then, this particular observation kind of put a nail in that coffin. So let me describe this observation. What you're seeing up here are two clusters of galaxies. So the fuzzy points are galaxies. There's one group of fuzzy points right here. That's one cluster. There's actually another group of fuzzy points right here. That's a second cluster. If you look at this in X-rays, you can see the type of stuff that Fritz Zwicky was looking at, which is the very hot gas in the cluster. Gas so hot that it's emitting light in the X-rays. And what astronomers see is that all this hot gas lies in between these galaxy clusters. So this red is the hot gas. It's right here. There's one cluster of galaxies here, the other cluster here. So that's a little bit strange. We'd expect the hot gas to be associated with the clusters. But what's happened is that there's been a merger between these clusters of galaxies. So the galaxies have galaxy clusters have basically passed through each other. So like that. Now, since the stars and galaxies are very far apart, they just pass through without any big influence. The gas, however, the gas actually ends up colliding. And when it collides, it heats up because of these shocks. It becomes very hot, and it also just kind of sticks right in the middle. So that's what you're seeing here, is this gas from this cluster collision. Okay, so astronomers looked at this and said, this actually gives us a really good opportunity, because if most of the mass in the universe is actually normal matter, stars and gas, we know that this gas actually contributes a lot of gravitational force compared to these stars. There's actually more mass in this hot gas right here than there is in the stars. So, yeah, that's surprising too. We also tend to think of the universe as being the stuff we see, the stars. Turns out there's a lot of gas out there too. So we can see it, we just have to move to other forms of light, like X-rays or radio waves. All right, so if most of the mass is in the gas, then we should be able to see that most of the gravitational force is coming from that gas. If there's no such thing as dark matter, it's just this modified gravity. Okay, so it sure would be great if we could actually detect that gravitational force. That's a little bit tricky, but it is possible. So to talk about that, I've got to introduce general relativity. So general relativity is this idea that Einstein put forth that says that gravity works by actually warping space-time. So if I have a very massive object, like the Earth or gas from a galaxy cluster collision, then that massive object is going to warp space-time around it. And then the reason that things orbit in gravity is because they're following these trajectories on this warped space-time. If you can think about a BB on a warped mattress. So the classic example is, imagine putting a bowling ball on a mattress. You get a warp. Bowling ball is your mass. The mattress is space-time. And you can imagine flicking a BB and having it go around in a circle, like those gravity wells. So this is the kind of new and improved idea for how gravity works, as opposed to Newton's idea. Now, this has all sorts of cool effects, this warping of space-time. One of those cool effects is that this warped space-time actually acts like a lens, just like glass and glasses act like a lens. So we call this gravitational lensing. If I have us here with our telescopes, and some massive galaxy out here, and I look at an object behind that galaxy, the light from this object is going to get warped as it goes around and actually end up heading back towards us. Just like the light as it goes through the lens and glasses gets warped and gets bent back. So the result is we see this kind of, rather than seeing just a small red blob when we look out here, we see a lensed image, this smeared out light. Here's a really nice example of a gravitational lens down here. We have a very massive galaxy here that's acting as our lens. And then there's this blue galaxy, which was probably a spiral galaxy, which is in the distance behind this galaxy. But the light from it, as it's come out, has been bent back towards us, and what we're seeing is the warped lens. All right, so this is great. This means that if we can detect lensing, gravitational lensing, that tells us about the gravity. So if I go back to my cluster, and I say I'm going to look for objects in the distance that were lensed, and use that to tell me where the gravitational force is coming from, where the mass is. It's a little bit hard to see here, but sometimes you'll notice that some of these galaxies are a little bit elongated, weirdly elongated. So they did a careful analysis of that, and they came up with this map here. So in the red, what you're seeing is where the hot gas is, just like that previous one. The blue, you're seeing where the gravitational force is coming from. And it's originating from where all these stars are. It's not caused by those stars, though. We can measure the mass of the stars. We know it's not as much as the gas. It must be coming from the dark matter associated with those clusters. So this is a little bit of a tricky thing, so let me see if I can summarize it. If there were no such thing as dark matter, and it was just that gravity was different at large distances, we'd expect that there would still be the strongest gravitational force at the center of where most of the mass was. However, we don't see it. We see two focuses of gravitational force, which are elsewhere. So what must be happening is that these clusters of galaxies, in addition to the stars and the gas, also have giant, massive halos of dark matter. Those halos of dark matter went right through each other, just the way the stars went right through each other. The gas ran into each other and shocked and heated up and ended up at the center, while most of the mass followed the dark matter and ended out where we see the stars. It's pretty cool. Okay, so what do we know now? What do we know about dark matter? We know it doesn't emit any light. It's dark. We know that it exerts a gravitational force. Okay, so it's matter. What can we do with that? Well, there are actually multiple theories for what could be causing this. I'm going to give you two, and I'll talk a little bit about the others. So one idea are machos. So macho stands for Massive Compact Halo Object. So what this is these are objects which exist in the halo of galaxies, so surrounding the disk of the Milky Way. There have to be all these objects. Then those objects have to be compact. So by compact objects in astronomy, we mean things like black holes, or neutron stars, or say planets like Jupiter that are just free floating out there. So this idea is that maybe what we're seeing as dark matter are kind of normalish matter, but in a form that's very hard to detect, this form of these massive objects that just don't emit much light. Like, say, the Milky Way is surrounded by all these black holes. So that's one idea. There's another idea, which is that dark matter is a type of strange elementary particle. One example of this strange elementary particle would be a WIMP. So that stands for a weakly interacting massive particle. So that's a particle that's about 100 times the mass of a proton. So it's massive for an elementary particle. It's not massive by our scale. And the idea here is this stuff can't produce light, and it can't absorb light either. It's got to be invisible. But maybe it can interact weakly through other ways. In particular, astronomers love puns, the weak nuclear force. Okay, so we have two competing theories, machos versus WIMPs. So there have been experiments to try and figure out which one of these theories is best. So the first idea was, can we detect machos? Can we detect these compact objects, these black holes or neutron stars that live in our Milky Way halo? It's hard to do because they don't emit light, right? How do you see a black hole? Well, we had this trick earlier where we wanted to know where all the gravitational mass was, and we used gravitational lensing. We can do the same idea to try and detect these machos. Now, these objects are very small, so they're not going to create a dramatic lens as they go in front of something, but they will cause, as your macho passes in front of some background star, it will cause more of that light to bend around back towards the Earth. What this looks like is that briefly this background star will become a little bit brighter. And then as the macho passes on by, it will dim again. This is called microlensing. So what astronomers did is they said, let us stare at all sorts of background stars, say stars in a neighboring galaxy, the Large Magellanic Cloud. We'll look at all these stars and we'll see if they ever brighten, briefly, because of this microlensing. You can imagine this is a tough experiment to actually put into place. You got a lot of stars, you have to very, very carefully monitor their brightness, you have to be able to detect this type of brightening as opposed to some other type of brightening, say the star had a flare. But they did this, and they detected some machos, but like that much, really small. Nothing that could account for the mass in the Milky Way halo. So this theory was exiled. Except, there's a little bit of a coda here, which is that machos are now, astronomers are starting to kind of nudge each other, say, well, maybe machos could still be a possibility for at least some of the dark matter, and here's the reason why. Did any of you hear of the announcement of the colliding black holes a couple of years ago? Yeah. So LIGO, the Large Interferometric something array, I'm forgetting, Gravitational Observatory, was looking for gravitational waves. These are warps in space-time that happen when two objects orbit around each other and collide. So, artist's interpretation here, obviously the black holes are a lot farther away from Earth than it looks like in this picture. But the black holes go around together. As they collide, we get this rippling wave that comes out. And since this is a gravitational wave, it's a wave in space-time itself. It actually causes space-time to expand and contract, expand and contract. And what LIGO was doing was, it was an observatory which was supposed to measure the expanding and contracting of space-time. Also a really hard experiment. But they got it working, and almost immediately they detected two black holes colliding. Two black holes that are about 30 times the solar mass. And the observations are right here. So there are two different observatories actually, because it's very hard to separate out these signals from just random background noise, like cars going by or logging happens near this observatory, and all of that can cause the thing to rattle. So they need two separate observatories, and they looked for this ripple in space-time, and they saw it. These signals right here, you'll see there are these curves, and they get closer and closer. That's because as the black holes cycle into each other, these ripples come faster and faster. Yeah?
On your previous slide and on this one, we look at stars and they're light years away. How fast does this happen that moves past, or that they collide and move past each other? It sounds like from the observatory that very quickly that they move past each other.
Okay, so the question is, we look at stars, they're light years away, but if we're looking, so timescales of the universe are long, but how fast is this timescale of the collision actually happening? Yeah, so we can only, the time period over which we see it, this is in seconds on this axis down here, so less than half a second when it's actually observable. Now, the merger of the black holes itself, these two things start very far away. They get close really slowly. So there's a long time when they're orbiting around each other and not quite merging, not yet merging, and that can last for billions of years. But we get to see the final stage, the half a second phase, when these ripples are strong enough for us to actually see. The ripples get stronger the closer these two things are. Okay, so what's this all leading up to? It's leading up to the fact that, guess what, there are 30 solar mass black holes out there, and there seem to be enough of them for them to actually produce collisions. We haven't been running LIGO very long, so it's maybe kind of amazing that we saw one. This is leading astronomers to wonder if maybe there are a lot more 30 solar mass black holes out there than we actually suspected. And this is meaningful because this macho detection experiment I was telling you about earlier, they really only looked for things that were 15 times the mass of the sun or smaller. Because when this experiment was conceived, the idea was that that would be what most of these objects were. They would be black holes that formed from massive stars, which would be around 10 solar masses, 15 solar masses. Or they would be neutron stars. Those are the remnants of slightly smaller smaller stars, so they might be around 4 solar masses, or they'd be like Jupiters. So you're looking at the low mass end. But now we're seeing black holes that are in this kind of higher intermediate range. These are weird black holes. They weren't really fully anticipated, at least not that there'd be a lot of them. There's this idea that maybe these black holes didn't form out of dead stars. Maybe these black holes formed at the very start of the universe, and right after the Big Bang. They're called primordial black holes. So what this has done is this has opened up a whole new possible field. So maybe machos are dead, or maybe there's hope for them yet. That's where we're at. All right, so what about WIMPs? That's this other idea. How about, and by WIMPs, I'm going to talk about more generally elementary particles that could cause dark matter. Axions is another potential model. How could we figure out if that's causing dark matter? One thing we could do is we could try and create them. One way physicists create particles is they take particles and they smash them together and they see what comes out. And when you smash particles together at very high speeds, you introduce a lot of energy. Einstein says that mass and energy are kind of interchangeable. During this collision, some of that energy can be transformed into other particles. And the particles you smash together can be broken up into different particles. So if you do enough of these collisions, you can create a whole zoo of fun, interesting elementary particles. So they've been doing this. I love that this is a huge area of physics. Let's smash things together and see what comes out. But it is, and these are serious scientists, so I shouldn't joke about it. They've been looking for dark matter, and they haven't come up with it yet. So that's been difficult. Maybe the idea is maybe we just haven't gotten down to, or high enough energies to produce these dark matter particles yet. So this is one line of inquiry, but it hasn't produced results so far. At least, it's produced a lot of null results. It hasn't produced positive detection so far. All right, so here's another thing we could do, is we could try and, this is called directly detect the dark matter. So the trick is, remember, these elementary particles aren't going to interact with, they aren't going to produce light, and they're not going to absorb light. What that means to a physicist is that they don't interact with the electromagnetic force. The electromagnetic force is also the same force that holds atoms together. Is the reason why I can lean on this table, because my atoms are not passing through the atoms of this table. This means it's very hard to detect these dark matter particles because most of the time they will just sweep right through us. In physicists speak, they have a very small, very, very small cross-section. They're invisible not just to light, but pretty much to touch, to interactions. However, we do suspect that occasionally, potentially, they would collide with a regular atom. Very rarely, but every once in a while. So that's what these physicists are trying to do, is they're trying to detect these very occasional collisions. And let's see. The nice thing is, even though these collisions are very rare, we've calculated that there are about 100,000 dark matter particles that pass through a square centimeter per second. So if you hold your hand up like this, and you wait a second, 100,000 dark matter particles have gone right through there. So, it doesn't need to be a ton of collisions, just occasionally. So they have these giant vats of xenon, liquid xenon, and they look for the occasional dark matter particle which collides and actually interacts with a xenon atom and causes the xenon particle, the xenon atom, to go off that way. And in the process, as it moves, it's going to emit a little bit of light, which we can detect on a photomultiplier tube up here. So these experiments are in process. They've not found anything yet. These are hard because there's also all sorts of other stuff that will go through your xenon detector. Things like cosmic rays, other elementary particles like neutrinos, and you have to separate out all of that from your very exotic dark matter. All right, so there's one final way that we can think of to detect these WIMPs, and it's actually the way which has been most promising so far. It's also the least direct way. This is called indirect dark matter detection. Okay, so here's another theory. What if dark matter particles occasionally not just collide with normal matter, what if they occasionally collide with each other, and when they do, they annihilate? This fits within our particle model, and we would expect this annihilation to take place where there's a high density of dark matter. So dark matter exists throughout our galaxy and beyond in this giant halo, but there's actually there's a higher concentration of dark matter at the very center of our galaxy, because there's a strong gravitational force there. There's actually a slightly higher concentration of dark matter wherever there's a larger concentration of mass. So our sun, also there's a very slightly higher concentration of dark matter there. So if you look at these areas where there's a high concentration of dark matter, then you should be able to potentially see evidence of these collisions. So what they've done here is astronomers have looked out towards the center of the universe, or sorry, not the center of the universe, center of our galaxy. And at the very center of the galaxy, we see gamma rays. This is our high energy light. And we can account for a lot of those gamma rays, but if we subtract out all our known sources, we're still left with this excess amount of gamma rays right at the center of our galaxy. Now, this could be dark matter, or the results of dark matter annihilating with itself, or it could be something else entirely. So this is a potential signature of dark matter, but there's a lot of stuff that happens at the center of the galaxy. A lot of stuff which is really hard to model. So it's hard to know if that's truly evidence of dark matter or not. Okay, so let's see. What do we know about dark matter? We know, based off of looking at how stars move in galaxies, that there is excess mass there that we cannot see, that doesn't emit light. This has been verified by looking at how much hot gas exists in clusters of galaxies. Clusters of galaxies are able to hang on a lot more hot gas than we would expect, given their stellar mass. And it's been shown that this stuff actually has to be its own type of matter, not just a change to gravitational laws, because we see that this matter, because the observations of bullet clusters show that this matter is not centered on the gas. Most of the observed matter is, it's centered elsewhere. And we've been trying to figure out what it could possibly be. So physicists and astronomers are trying to come up with a model for matter which doesn't produce or absorb light. One possible model would be, normal type matter in exotic circumstances, something like black holes. But we haven't been able to detect any of these. So physicists have mostly ruled out this macho model, but there's a possibility that maybe if we change the mass range we're looking at, maybe that could contribute to some, or even all of the dark matter. The other possibility is maybe dark matter are weird elementary particles that just don't interact with light electromagnetically. So, been trying to detect it, but for obvious reasons, dark matter is hard. It remains dark. All right, so I think this is actually a pretty good break point, and we will start up again with dark energy. Thank you. All right, so trying out a new microphone. How's this working? Yay, okay. All right. So if you thought dark matter was mysterious, wait till you hear about dark energy. All right, so to talk about dark energy, we're going to go back to Einstein. He seems to be coming up a fair amount in this talk. We talked about Einstein's theory of general relativity, how mass warps space-time. And Einstein didn't just postulate this, he took it a step further. He said, okay, so if mass warps space-time and the universe is filled with mass, what's that going to do to the fate of the universe? How's gravity going to affect our universe? And he wrote down his equations, and he came up with something which is actually a little bit intuitive, which is if there's all this mass out in the universe, which is all gravitationally attracted to each other, it should cause the universe to curl back in and shrink. So all this mass and the gravitational force between that mass should bring everything back together again. This makes sense because it is the same reason when I drop this, it goes to the Earth. The only difference that Einstein came up with is that not only is our mass coming back in together, it's basically pulling space-time with it. So he said the universe should be shrinking if it has all this mass, or at least it should be eventually going to shrink. Maybe. It should be decelerating, to be technical. So he wrote out this math, and he said, this doesn't seem right. Clearly the universe is static. Or maybe not clearly, but based off of all ideas at that point, the universe was static. So philosophically speaking, the universe should not be changing. And he was certainly not the only one to think this, and really thinking along the same lines as basically the entire scientific and philosophical community. So he said, let me fix my equations. I'll just add this constant here, which repels gravity, kind of an anti-gravity type thing. And if I add that in, then that will completely balance out gravity, and that will result in a static universe. Okay. As fate would have it, not too long later, this guy comes along. So this is Edwin Hubble. And Edwin Hubble, remember back when I said that we haven't actually known about the existence of other galaxies for that long? He's the guy who solved that problem. In about 1920, what he's doing is he is looking at what were then known as spiral nebulae, these fuzzy spiral things in the sky, and he's making measurements of the distance to them to try and determine, are these little gas clouds which exist within our galaxy, or are these other galaxies? And based off of these distance measurements, he's able to determine that these are indeed other galaxies. So that's cool enough right there. But then, in doing these types of measurements and looking at his data, he decides to plot the distance to these galaxies and along with how fast these galaxies are moving. So he comes up with a diagram that looks like this. This is called the Hubble Diagram for obvious reasons. And along the x-axis, this is distance. It's hard to read because this is the original one. This was published in 1929. And this is on the order of 1 million light years right here. Yeah, and measured in parsecs. So this is distance to these other galaxies, and this is velocity at which these galaxies are moving. And one thing to take note of is the scale here. This is 500 kilometers per second, or close to 1 million miles per hour. So he's seeing these galaxies, and they're far away, and they're moving away from us really, really fast. Not only that, the further away they are, the faster they appear to be moving. So what this plot implies is that we're here and all these other galaxies are moving away from us, which is kind of insulting when you think about it. It also poses a kind of a philosophical problem for astronomers. Astronomers have gotten into some trouble in the past with assuming we are at the center of the universe. Turns out the Earth is not the center of the solar system. Turns out the solar system is not the center of the galaxy. Edwin Hubble is not going to say, clearly our galaxy is at the center of the universe. And this is what's called the Cosmological Principle. It says that we are not in a particularly special place in the universe. It is a principle, it's not something we can prove, but so far it seemed to hold pretty well. So, can we come up with an explanation for this diagram that allows us to not be at a special part of the universe? Well, we can. We just have to assume that the entire universe is expanding. So, it's hard to visualize because we live in a three-dimensional world, and four if you count time, and we think in three-dimensional terms. So it's hard to imagine the 3 dimensions expanding into some fourth dimension, fourth spatial dimension. So let's make everything easier, and we'll assume that our universe is 2-dimensional, like the surface of a balloon. And all of our galaxies exist on the surface of the balloon. As this balloon expands, all the galaxies get farther and farther apart. So if I lived right here, then I would notice that, these galaxies have moved away from me. Now they're over here. And they are continuing to move away from me, and if I were to wait a while, they'd be even farther away. But if I lived in this galaxy, I'd say the same thing. I'd say, gosh, these guys have been moving away from me. And look, they're going to continue moving away from me. So this is a very elegant way to say, perhaps everybody's moving away from me, but it's also moving away from everything else too. The universe itself is just expanding. And it provides a really elegant solution to this other aspect of the diagram, which is that the farther away things are, the faster they're moving away. So this is kind of hard to visualize in 2 dimension. So let's take our universe and we'll shrink it down to 1 dimension. So now our universe consists of a line of galaxies. Let's say we're in galaxy C. So here it is at time now. And some time later, we're still here, but these other galaxies have moved away from us. And you'll notice that this galaxy here has moved farther away from us than this galaxy here has. So an expanding universe not only abides by the cosmological principle, it can also explain why the further away something is, the faster it appears to be moving away from us. So this is really cool, and other observations have borne it out. If we were to add a lot more plots or points onto this diagram, other galaxies, we can send you to see this line, where the farther away something is, faster it appears to be moving away from us. And this also goes out to greater distances than Hubble's original diagram, which I think was around this region right here. Now, one important aspect of this plot is the steepness of this line. It has a slope, right? And if it were a steeper slope, then that would mean that things were moving faster away from us. If it were a shallower slope, then things would be moving away from us more slowly. So the slope of this line here tells us how, in some sense, how fast the universe is expanding. So if we measure this slope, then we'll get an idea of the rate of expansion of the universe. Pretty cool. Yeah?
The width of that line, is that due to errors in measurement, or is there something else going on there that causes some to move away, seem to move away slower than others?
So some of it would be certainly uncertainty in measurement. Oh, sorry. Question was, what causes this width of the line, or the scatter in this plot? So some of that would be due to errors in measurements. In particular, distances are very hard to measure. We'll talk a little bit more about how we measure distance later on, but for now let's just say they're hard. But the other thing is that in addition to this overall expansion of the universe, galaxies can have their own particular motion. I showed you those images of clusters of galaxies earlier. And in those clusters of galaxies, all those galaxies are interacting gravitationally with each other. So they're actually orbiting around the center of the cluster. So there's additional movement the galaxies can be undergoing. Yes?
I'm sorry to interrupt, but I know this is the question that everyone wants to ask. On your balloon diagram, a neutrino is shooting through, so it goes through the outer skin of the balloon. So it does go through the middle of something. What's inside the balloon?
So
And you've been asked that before, and I'm not going to like your answer.
So the question is, what is inside of the balloon? And what this really is saying that we don't have a good model for our universe or the expansion of the universe. The idea is that we tend to think, because we live in a three-dimensional universe, we think of folds happening embedded within that three dimensions. So we imagine a two-dimensional object folding and embedded in some other dimension is how we see that fold. Or we imagine a string curving and we notice that curve within a two-dimensional plane. But that's artificial. That's just based off of how we've grown up interacting with the world. You can actually have curves without a larger embedded dimension. And we have no reason to think that our universe is not all that there is, that it doesn't exist in them. There's no reason to believe that there's a larger dimension that's embedded in. It may just be curved or flat as it is. But to make that even more to your point, so that's kind of what is there inside of the universe? Or, within this curve? Quite nothing. The universe is, to the best of our knowledge, all that there is. Some astronomers speculate about multiverses. So, there's some reason to speculate. But there has been, to our knowledge, no way of interacting with anything outside of that. This gets really weird when people ask, well, what happened before the universe, before the Big Bang? And it's the same problem. Time is another dimension. Time was not before there was a universe. And I hate using the word before there, but time began, and again, began's a weird word. So I think this gets at the difficulty that we have our own way of interacting with the world. It's not necessarily how the universe itself works.
Thank you for clarifying that.
Thank you for asking the question. You can see I could just go on this forever. But to take it even a step further, you asked about the neutrino. So let's say even if we were embedded in some bigger dimension, neutrinos exist within our universe and they're only able to travel on the surface.
What are the neutrinos inside that thing doing?
Well, we don't know that there are, but presumably they can't travel to us or else we would have seen them.
Okay, thank you. I knew I wouldn't know like that.
I shouldn't have pushed it, should I? All right, so let's see. So we have an expanding universe. This, there's an urban legend that Einstein called his fix to his equation to keep the universe static, his biggest blunder. It's probably actually not, he probably actually didn't literally say that, but he did regard it as an error. He assumed that the universe was static, because everybody assumed the universe was static, but it isn't. Again, our ways of assuming that things are, we assume the universe is static because in our experience the universe is static. But that's a very limited perception. It turns out in this case to not be true. Okay, so if the universe is expanding, what does that tell us about its future and its past? So astronomers thought about this, and they went back to Einstein's equation without the fix, and they said, what are the possibilities of how this expansion could be taking place? Well, one possibility, in all cases, we have to imagine that gravity is pulling everything together. Gravity wants to contract. So there's one possibility, which looks like this, which is the universe starts off expanding and then contracts back together again. So we have a big bang, and then gravity brings it all back together again into a big crunch. There's another possibility though, which is if I could throw this really, really fast, I could actually get it fast enough so it would never come back, like a rocket, right? So I can throw it, which I'm not going to do because it would burst through the ceiling and I don't want to do damage to the library. So we'll forget that demo. But I could throw it fast enough that it would never return. It would just, because of gravity, slow down a little bit as it went out. So it wouldn't remain as fast. It would slow down but never come back together again. And that's what's happening in these two diagrams here. So astronomers ask, well, it sure would be great to know if we're going to end up in a big crunch or not, right? That'd be a really excellent bit of information about the universe. This is where the fate of the universe comes into play. It would also be nice to know about the age of the universe. If you look at these diagrams, you'll notice that this universe, which contracts, is actually younger than this universe, which expands forever. And that's because we have a measurement of the scale of things right now, and we have a measurement of how fast the expansion is happening right now. So depending on how fast it used to be, that tells us how long it took to get as it is now. So if this is the idea, you're at home, your friend knocks on your door, says they've been coming from their home. If they figure out they've been walking, that probably means they've been, it's taken them 15 minutes. If they drove, you can extrapolate they left home 5 minutes ago. It's the same idea. All right, so we want to measure which of these universes we live in, or at least that's what Adam Rees wanted to measure. Now, to do this, I said earlier on that the slope of the Hubble diagram told you the rate of expansion. That actually tells you, that tells you its current rate of expansion. But we want to know how fast it used to be expanding. Did it happen to be expanding really fast? This case where I tossed the ball really hard? Or did it used to be expanding more slowly? So how do you measure that? In astronomy, when we want to look at the past, we look really, really far away because it takes some time for light to travel. So this means that if I look out at the sun now, I'm seeing the sun as it was 4 minutes ago when light from it left. Or is it 8 minutes? I always get that one confused. If I look out at Alpha Centauri, which is 4 light years away, I'm seeing Alpha Centauri as it was 4 years ago. If I want to see the universe as it was 10 billion years ago, I have to look at objects which are around 10 billion light years away. Which is a little bit more complicated than that, but close enough, you get the idea. So wouldn't it be cool if we could measure the Hubble diagram at really great distances? So that's what Adam Rees did with his team. And they want to measure the slope of Hubble's law very early on in the history of our universe. Now, the trick is getting the distance to those objects. Turns out that velocity is not too hard. For velocity, astronomers measure the Doppler shift, which is basically this phenomena where something is moving towards us, all the light waves get scrunched up together. This is just like when a siren is heading towards you, it sounds very high-pitched because all the sound waves are getting scrunched together. If it's moving away from you, the light waves get spread out, just like if it's moving away from you, the pitch goes down as the sound waves get spread out. So we can measure velocity really easily. Distances are hard. One good way to measure distances is to look for objects of a known luminosity, a known amount of light that they're emitting, and see how bright they are. This is called a standard candle. So if I know how bright a candle is, or if I know how much light a candle emits, and it looks very bright, that candle is close to me. If it looks dim, that candle is far away. I could do a very small amount of math to go from how bright this candle appears to how far away it actually is, provided I know how much light it's emitting. It's that, provided I know how much light it's emitting, bit that is hard. So to do this experiment, what we need are objects of known brightnesses that are really, or known luminosities that are really, really luminous. One thing to do are supernovae, in particular a specific type of supernovae. These are supernovae that form when the remnant of a star, called a white dwarf, ends up accreting on some extra material from a nearby star, and it accretes on so much material that it can no longer support itself, and it implodes and causes this huge burst of light. So it basically entirely ignites. Since this ignition happens at the same critical mass, then we believe that it is always the same luminosity. So you're always creating the same type of explosion, if you like. So he looked for all of these, well, he and his team looked for all of these supernovae, measured how the brightness of these supernovae, used that to figure out how far away they were, and then measured how fast they were moving to get at the Hubble diagram at great distances. So you can imagine the Hubble diagram, and this is actually more confusing than this plot appears. This is velocity here, distance here. So I flipped these axes from before. Earlier it was distance here, velocity here. And if I look for something far away, if the universe had always been expanding at the same rate, then the slope would always be the same. So these out here are far away, so they must be early in time. If my universe was faster in the past, is currently decelerating, then if I look really far back in time, the slope, then the slope, which looks shallower here, but remember I flipped my axes, was actually steeper. So maybe the easier way to say that is, notice this has a higher recession velocity than what I would have expected from normal. So this says that in the past things were moving faster. This would be a decelerating universe. If instead I notice that things used to be moving at a slower recession velocity than I would have expected, then that means that in the past the universe was slowly expanding, and now it's expanding faster. Okay, so he made these measurements, and this is the plot from, I do not have when this paper came out. It was in the 90s, 1990s. And this is distance up here. This is velocity. So it's exactly like that plot I just showed you, the schematic I just showed you. And if you look very carefully, you'll notice that these points tend to curve up from a straight line. In other words, this is an accelerating universe. I didn't show you a diagram of an accelerating universe before because no one thought we would find it. So in the past, faraway objects were traveling at slower velocities than we would have expected. So let me add that to the plot that I showed you before. So now, here's a recollapsing, here's one where I toss a ball really, really high. Here is a universe which has been expanding at faster and faster speeds as time goes on. So this was totally unexpected because we thought we knew everything that was going on in our universe. We thought that we knew gravity, we thought that would dominate this recollapse, and yet it isn't. Gravity might be trying to pull things back together, but it's clearly being overpowered by something else. And that something else they call dark energy. The dark here doesn't emit light, it means dark as in hidden or mysterious or unknown. So we don't know what it is which is causing our universe to accelerate. Yeah. Here's another way of showing that same diagram. Let's see, this is time. This is time back in the past. This is time into the future. This is us now. This is the average distance between galaxies. So we are right here, and in the past, the average distance between galaxies was smaller. Each of these curves represents one of those different universes. So this gold curve here, that's our accelerated universe. So in the past, the distance was smaller, and in the future, the distances are going to be greater, and even greater than we would have expected than these other models. The other thing, you'll notice the age, right? Now the age is much longer. Let's imagine your friend comes over to visit, and she arrives and she's jogging. And you think it only took her a short amount of time to get over. It turns out she actually walked very slowly for the first half of it. I mean, she's been traveling for much longer. So dark energy changes our impression of what's going to happen in the future. It also changes our idea of what happened in the past. We're now presented with a much older universe than we anticipated. And this future is actually maybe a little bit worrisome. There's this idea if the universe keeps on expanding at a faster and faster rate, maybe we are in store for a big rip. This is the technical term. It certainly means that as time goes by, less and less of the universe is actually going to be visible to us, because things are going to be moving farther away than we'll be able to see. Let me just finish my slides and then I'll take questions, if that's okay, because I only have one more slide left. Okay, 2 more slides. So there's this question, well, what is dark energy? What could be causing it? What do we know? We know it opposes gravity, and we know that the rate of expansion is increasing even as the universe gets bigger. This is odd, because this means that even as I spread this, whatever it is, out over broader distances, it doesn't dilute. If I were to release a gas into this room from a small container, it would dilute as it filled up the bigger room. This doesn't happen with dark energy. We believe that maybe the dark energy comes from the vacuum of space itself. And that's why as space gets bigger, this stuff just keeps on going. This takes us back to Einstein's little fix at the end of his equation to keep the universe static. We call that the cosmological constant. And it is a really good model, as it turns out, for what dark energy could be. Only now it's causing the universe to expand at an accelerated rate, as opposed to that, just keeping it stable. So how this energy could come out of the vacuum? Some quantum theorists imagine that particles can spontaneously come in and out of nothing. So if you have a particle and its antiparticle, then those two things perfectly cancel out. So they could be nothing, or they could spontaneously appear, and then they could come back again. And we know this happens. The idea is that maybe there is an energy associated with this. So people have done some calculations, and it's far, far too much. So this seems like a promising theory, but we haven't worked out the math yet. Yeah, so that's kind of where we are with dark energy. At this point, there's a lot of theoreticians trying to figure out what could be causing this. There's some effort to try and take better measurements of what this is. And hopefully there will be a breakthrough. But we're not to the point yet of coming up with experiments the same way we are, to detect it the same way we are with dark matter. Okay, let me take you back to this plot here. So we all started off knowing about this part, the 4%, right? You came into the room and you knew about yourself and your atoms. We talked about this part here. This is the dark matter, this extra matter that seems to be holding galaxies together, providing stronger gravitational force than stars alone could account for. And now, all this other energy, which is clearly really powerful because it's causing the universe to accelerate as opposed to coming back in together because of gravity. If we know that energy and mass can be transformed into each other because of Einstein. Energy equals mass times the speed of light squared. If we transform our measurement of dark energy into a mass measurement, Turns out it's 76% of our universe at this day. So there's a lot left to study, I guess, is the final, the final conclusion. There's much more to be done. Okay, now I'll take some questions.
I wonder if some of this change is affecting our climate control.
Well, so this is, so what's happening is that although dark energy, question was, could some of this change be affecting climate control? So I should say that dark energy is incredibly powerful. However, it's only powerful in regions of the universe that are relatively empty. I told you earlier we don't live in a particularly special part of the universe. It's not quite true. Living on the Earth itself means that we live in an unusually incredibly dense part of the universe. Because we got the Earth and us in the solar system, most of the spaces is effectively a vacuum. In this region of high density, dark energy is negligible, as actually is dark matter. Yes?
Is there any way to know whether this expanding universe that's supposed to be going on forever is something that'll keep going on forever? Or is this part of the cycle of expansion, contraction, bang, expansion, contraction? Has this been going on forever and ever?
Okay.
Over and over and over?
So the question is, do we know that this expansion will happen forever, or could it be part of a cycle? And I can say from what we know now, the components of the universe that we've been able to measure, light, matter, dark energy, all of that would result in expansion forever. However, we did not know about the existence of dark energy till now. It's possible that, and if we'd existed 12 billion years ago, we also would not have really known about the existence of dark energy because it wasn't dominant then. It's possible that 20 billion years from now, some other thing could come into play. So I'd say to the best of our possible knowledge, we will expand forever, but hard to know for sure. We'll wait a while and see. Yes?
I always try to understand the mathematics, that's my crutch, and sometimes the language. And I couldn't really distinguish the coasting from the critical. It looked to me like the coasting was a cone, the critical may have been a conic section. But critical normally means one particular value, and here the critical seemed to be more generic. So why is it called critical?
Yeah, so I kind of elided that. So there is a particular escape velocity, just like on Earth there's a particular escape velocity between return and never return. If we were to think in terms of orbits, this is your parabolic orbit, which is a conic section. This is your hyperbolic orbit, where it's faster than that escape velocity. This is actually a really extreme variation because it looks like they've put these lines pretty much straight. This would be many, many, many times higher than your critical velocity. I'm sorry, I didn't state the question there, did I? The question was, what is the, this says it's a critical universe, but what does critical actually mean there, mathematically?
Going back to that pie chart, you answered the 75, how we know, I think you answered 74% dark energy, because we know the 4% and the 22%. How do we know the 22% when observation has to be so indirect? And how do we know how large the pie is?
Well, so there's one very important, question is, how do we actually put numbers on these, and particularly the 22%, which is so indirect? There's one figure which I didn't show because, just for time reasons, that's very important, and that's an image of the cosmic microwave background radiation, which is the residual glow from the Big Bang in all directions. This provides us with very, very precise measurements of the universe soon after the Big Bang. Within that is a very precise measurement of the matter content of the universe encoded in that. That tells us where dark matter, that's really how we get those numbers of dark matter. Yes?
Energy is a word I understand because I'm addicted to electromagnetism. Okay, matter too. But I think I understand a little bit more about what dark matter might mean after your talk. I'm completely baffled by the use of the word energy to describe the thing of the 74%.
Okay, so the question is, how does energy relate to this acceleration of the universe? Maybe that's
the term.
Yeah.
I think it should be called
Yeah, so, and that's because I've tended to talk about this in terms of the force, like this is a force opposing gravity. What we actually care about, though, physically, is what is generating that. So what generates, there's a close relationship between energy and force, where changes in energy are what cause a force. You can think about this on top of a hill. If I were to put the marble, if it's right at the top of the hill, there's no change in topography, so it stays where it is. If it's off to the side, then it feels a force downward. So so the energy itself is what generates the force there. Without being too technical, just because of the time and the context, for there to be this force which is opposing gravity, we know there's a force because of the acceleration. Acceleration, if you remember back from Newton, F equals ma, force equals mass times acceleration. Acceleration indicates a force, but force has to arise from an energy. So this is getting at kind of the underlying cause of that. Yes?
I'm just trying to, wrap my head around this, but I can kind of picture all of this matter reaching an escape velocity, which would mean that the other matter around it loses its gravitational power over, its neighbors. And then it reaches a point where there's a vacuum, which then would speed things up, would pull things in if the vacuum is all around. But I just, does that make any sense? And another thing, is there a book you can recommend for someone who... Anyway, my first point, I can kind of picture if our universe is surrounded by a void, a true void, it would make sense that it's being pulled into a void. And the original Big Bang was big enough to reach escape velocity so that all the matter could get out to that void.
Okay, so
how am I doing?
The question is about how did the Big Bang cause things moving into some void to reach how does the escape velocity originating from the Big Bang function within this depiction of a void surrounding the universe?
Yeah.
So this is again what difficulty in imagining our universe. The Big Bang happened everywhere. Everywhere in the universe experienced a Big Bang. The empty void-like parts and the filled parts, like where we are. Though everything was pretty smooth right at the Big Bang. Exceptionally smooth at the Big Bang. So everywhere in the universe experienced that. There's no kind of expanding into anything. One way to say it, this universe was very, very dense and very small. And now it is low density and big. But there's no space that it's moving into. It itself encompasses all space. So escape velocity, this is an analogy which works pretty well between kind of how we think of orbits on Earth to how the universe actually expands or contracts. The rate at which the rate at which the separation between objects is growing, that's the equivalent of the velocity as opposed to the distance being traveled in some amount of time. So what you want is for the separation between objects to grow so fast that it outraces the gravitational force pulling those objects back together.
Charlotte, I'm sorry to interrupt. As you can see, you are talking about a fascinating subject, and I think we could stay here for hours asking questions and listening to your answers, but we really want to thank you so much for introducing many of us to this subject. Thank you so much. So I want to invite you to come back next week to hear the third class in Mike Latham's series on the wider history of the Vietnam War. Now, before you leave, remember to turn on your cell phones and turn off your T-coils, and we'll see you next week. Thank you.